Alright, the function k from x times x to real numbers where x is any set is called a kernel function if it is symmetric and positive semi-definite. Here symmetric means k of xy is equal to k of yx, and positive semi-definite means for any set of n elements of x and any set of n real numbers where n is any natural number, this quantity is always greater than or equal to 0. In this video, we study some examples of kernel functions and how to construct a kernel function from other functions. Okay, let's start. By the way, if we regard this k of xi, xj as a matrix, n by n matrix, then this definition of positive semi-definite is equivalent to the definition of positive semi-definiteness of a matrix. That means, so if we construct a matrix, k of x1, x1, k of x1, xn, k of x2, x1, and so on, xn, and k of xn, x1, k of xn, xn. So if we construct this matrix, n by n matrix, then if the function k is positive semi-definite, then this matrix is also positive semi-definite. So our first example is based on a matrix. Suppose we have a matrix A whose elements are A, I, J. So this is an n by n real matrix. Then we can define a kernel function based on this matrix. First, let's define the set I, which is the set of natural numbers from 1 to n. Then we can define the function k from I times I to real numbers by defining k of ij is equal to aij, where aij is this element, ij element of the matrix A. Now, this function k is a kernel function if matrix A is symmetric and it is positive semi-definite. So k is a kernel function if and only if this. Next example. Suppose we have a function f from x to real numbers. Then we can define a kernel function from x times x to real numbers by k of xy equals to f of x times f of y. Now this is a kernel function. Symmetry is obvious. Of course, this is equal to f of y times f of x, which is k of yx. How about positive semi-definiteness? To see the positive semi-definiteness, we take this summation ij from 1 to n, ci, cj, they are any real numbers, and k of xi, xj. By definition of this function k, this is equal to ij, ci, cj, f of xi times f of xj. But we can split the summation over I and over j, so this is equal to I from 1 to n, ci f of xi times j from 1 to n, cj times f of xj. But this is, I and j are just indices, so this is actually equal to, they are actually the same sum. So this is equal to ci, sum over I, ci times f of xi, everything squared. Of course, this is a square of a real number, so this is always non-negative. Therefore, it is positive semi-definite. So we can construct a kernel function from any univariate function on x. Next, we show the sum of kernel functions is also a kernel function. So suppose we have two kernel functions, k1 and k2, from x times x to real numbers. Then if we define k1 plus k2 xy as k1 of xy plus k2 of xy, then this new function k1 plus k2 is a kernel function. Again, symmetry is obvious because we are assuming k1 and k2 are both kernel functions, so they are symmetric. Yx, so this is k1 plus k2 of yx, so it's symmetric. What about positive semi-definiteness? This is also easy. So take sum ij, ci, cj, k1 plus k2, xi, xj. So by the definition of k1 plus k2, which is this, so this is equal to ij, ci, cj, k1 xi, xj plus k2 xi, xj. So if we expand this, we have ij, ci, cj, k1 xi, xj plus ij, ci, cj, k2 xi, xj. But by assumption, k1 and k2 are positive semi-definite. So this is always non-negative, and this is always non-negative. Therefore, their sum is also non-negative. Therefore, k1 plus k2 is also positive semi-definite, and it is a kernel function. So we can construct a kernel function from as the sum of two kernel functions, or two or more kernel functions. And next example, suppose phi is a function from x to the n-dimensional real vector space, and we assume the inner product in the vector space also. So Rn times Rn to real number. So this is the inner product. Then we can define a kernel function x and y as the inner product between phi of x and phi of y. Again, the symmetry is obvious, so let's show the positive semi-definiteness. So we calculate this double sum, ci, cj, and k of xi, xj. So applying the definition of this function k, we have ci, cj inner product between phi of xi and phi of xj. And we distribute this cj to the second place and ci to the first place. Then this becomes sum over I, ci, and phi of xi, and sum over j, cj times phi of xj. Now, I and j are just indices, so actually this sum and this sum, they are the same sums. So this is actually equal to the norm of this ci and phi of xi, norm squared. Of course, this is greater than or equal to 0. Therefore, this function k is positive semi-definite. So as in this example, somehow by mapping the set x to n-dimensional real vector space, we can construct a kernel function like this. Now, before explaining the next example, let us review the definition of a reproducing kernel Hilbert space, or RKHS. Let X be any set and H be a Hilbert space. Hilbert space consisting of functions on X. Then we say this H is a reproducing kernel Hilbert space if and only if, by definition, for any element f in H and any element x in the set X, there exists some function kx in H such that f of x, the application of function f on x, is equal to the inner product between f and kx. And this kx, the function kx, is called a reproducing kernel. Now, let's go to the next example. Let Hk be a reproducing kernel Hilbert space. Here, this k signifies the reproducing kernel. And let us define the function k of x and y as ky of x. Here, this ky is a reproducing kernel at y. Okay. Then this function k, this bivariate function k of x and y, is a kernel function. So let's show that this is indeed a kernel function. First, let's show it is symmetric. So first of all, this ky is a reproducing kernel, is a function in Hk. Therefore, there exists some function which is a reproducing kernel, kx, such that ky of x is equal to the inner product between ky and kx. And of course, this inner product is symmetric, so we can swap the order, kx and ky, but this is equal to, by definition, of the reproducing kernel, this is equal to kx of y, which is equal to k of yx. So this function k is symmetric. So let's summarize this. So this is actually equal to kx of y, which is equal to k of yx. And next, let's show the positive semi-definiteness. So we take this double sum, ci, cj, and let's see, k, xi, xj. So by the definition of this function k, we have ci, cj. So k, first we put xj here as subscript and xi here as an argument. Now, this is equal to, by the definition of the reproducing kernel Hilbert space, this is equal to the inner product, ci, cj, inner product between k, xj and k, xi. Okay, now let's distribute these coefficients, cj to here and ci to here. So this becomes, let's see, so inner product between sum over j, cj, k, xj, and sum over I, ci, k, xi. Now, again, this j and this I, they are just indices. So this sum and this sum, they are actually the same sum. So this is equal to the norm of cj times kxj, sum over j, norm squared, which is, of course, non-negative. Therefore, this function k is also positive semi-definite. Therefore, it is a kernel function. So, in a reproducing kernel Hilbert space, the reproducing kernel is indeed a kernel function. Alright, that's all for this video. See you next time. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.